Hey everyone, this is Enrico with Emil. Today we're going to talk about a detail that came up on social media. I'm not doing this video to criticize anyone, it's just to bring the conversation up and learn from actual building science as we analyze this detail. If we take a closer look, we have a 2x6 wall upstairs with continuous exterior insulation, and we have a foundation wall and a conditioned basement below with interior insulation. As we dive deeper, we can see that you have some cellulose insulation at the basement wall, inboard of some polyiso insulation. This is the yellow stuff that you see here. It's polyiso boards. So you have insulation on the inside of the concrete, on the inside of the rim, and then some spray foam. And on the outside, you have your exterior wall with some mineral wool or rock wool exterior insulation. And at the where the wall hits the ground, we have some stone veneer that is backed with some additional insulation, again, some polyiso here to prevent thermal bridging. If we switch to the isothermic view, we see that things start to look a little bit weird. You see all of the isotherms are on the inside and they're pretty disturbed in this region. If we switch then to the intensity of the heat flow, we have a pretty intense heat flow at the bottom. Here, that's because that is where our exterior insulation stops, and that is normal. But we also see a lot of heat flow going through the wood in this position, which is not what we would expect typically, because wood is not very good at conducting heat. And looking at the heat flow direction, we see very clearly that the heat is drawn by the flashing detail in this position. If we zoom further in, we can see how intense the heat flow is where the metal flashing is. This is a 24 gauge aluminum flashing detail, and it would be very similar even if you had stainless steel, just because metal is very good at conducting heat. So when we have exterior insulation, we really need to start rethinking our flashing details. If you look at the direction of the heat flow, the arrows, you can really see that the aluminum flashing detail really sucks heat from behind the exterior insulation and delivers it to the outside, becoming a highway for the heat to escape. This is very evident in the direction of the heat flow. And this is what causes an intense heat flow. You see, when it is all solid blue, that's the insulation. And that is where you have very little heat flow for the heat losses. But when we have the metal flashing, this becomes a very preferred highway to get out. And this is what causes the isotherms to be so disturbed, as we see here. And if we zoom back out, looking at the areas, this is what the detail we were looking at. And the disruption of the isotherms that we were talking about is caused by that metal flashing detail. It's also a case where the foundation wall steps up and impacts the insulation level. So you have two areas or two causes of thermal bridging. One is the concrete, and the second one is the aluminum flashing detail. And when you have the two of them combined in a spot that is a typically difficult construction detail to begin with, that is where you have risk for molding condensation to happen. So there are better ways to do that. An alternative is what looks like this, and it actually looks so similar to the previous data that I actually had to zoom in and see if I had the right file open. And it's very much similar flashing detail, but we stopped the metal flashing short of getting too much into the insulation. And this part of the flashing can be done with self-adhered flashing details with tapes or liquid applied, but as long as it is not metal, this thermal bridge effect will be eliminated. If we switch to the heat flow intensity, you see that the heat flow is pretty intense within the metal flashing, but because the metal is cut short, that thermal bridging doesn't have a chance to connect to the concrete stem wall. And so we have an actual continuous insulation. You see that the intensity is a fraction of what we had before, and the thermal bridging effect does not really happen because we cut our metal short of getting into the insulation. Once we switch to the isothermic view, we see the isotherms are now continuous between the insulation below and the insulation above. Having continuity means that you can eliminate the effects of thermal bridging, including molding condensation. To summarize, we do not need to reinvent the wheel. We just need to be aware of all the issues that we have in construction. Flashing is very important, but so is avoiding thermal bridging. And focusing only on flashing details may leave your flank exposed to having thermal bridging prone details like we saw at the beginning. And you just need to look at these details in closer depth.